Hey guys, I hope you're doing well. Hope you haven't missed me too much. This time, if you're an old timer on my channel, you're going to notice that this is somewhat different from my usual content here on YouTube. And this is because I'm trying to start going into some other directions as well. I'll keep doing Void Linux videos and Emacs videos and all this kind of stuff. But I also want to cover some of my personal projects. Now, this has been one of them. This is one little presentation that I have on a tool called Nornir. And this is mostly related to network automation. So for people who don't know what that is, essentially it's the idea that you can use software in order to to automatically provision and deliver configurations to your network devices. So things like routers and switches and firewalls, etc. Now, Nornir is one such tool in that ecosystem, I guess we can say that. And the idea here is that you can use it just like you would use something like Ansible. So to have a multi-threading, inventory-based controller for your network. And the main difference anyway, that I would say between Nornir and Ansible is that while Ansible uses a domain-specific language, that is, you write playbooks in YAML, with Nornir you have a bunch more control because you're writing your automation in Python. So this is what I will give as an introduction. We'll see what that means in a second. Now, in order to better show off this example, I've come up with this little scenario, which is a very common use case actually in service provider networks. That is layer 3 VPN provisioning. So the idea of an L3 VPN anyway is to provide IP connectivity between the different sites of route of a enterprise network. So here on this example, I actually have two locations. Here on the left, I have London, and we're supposing that there are two companies in London. There is the blue company called Beta, and the yellow company called Acme. And here on the right, we have two other locations, two other enterprise sites. So we have Acme, the yellow company once again, and Beta, the blue company once again. Now, here's what I would like to do as I guess as the IT for this company. I would really like to have those subnets. So let's say that I have the 192.168.10/24 subnet here on London. I would really like this subnet to be able to reach the 192.168.2.0 subnet here in Rome. Now, in order to do this over an MPLS network, you're usually going to use something like a layer 3 VPN. So the idea is that I'm going to establish essentially a BGP neighborship between the PE routers, which are the routers that connect the customer to the MPLS core. And then I'll use the BGP to transfer over the prefixes that I receive from the client. So here in between the client, the customer edge, and the provider edge, I'm going to configure OSPF. In this case, this is how the client is going to communicate networks. The OSPF networks are going to be redistributed into the provider's BGP, and the provider's BGP is going to communicate those routes to its peer router. We're going to call it that. And then the same thing happens. So the BGP here is going to redistribute routes into OSPF here. And I'm going to receive routes from the site in London in the site in Rome. And because this is done over VRFs, I'm actually not mixing up the routes. So this is very important because if you take a look at, for example, this router 2, you can notice that it's receiving two identical routes, you could call it. It's receiving a 192.168.10 from Acme, and it's also receiving a 1.0 from Beta. How is it not mixing those up? So internally, in terms of the connectivity here, it's actually separating the physical interfaces into separate VRFs. So this interface is going to be associated to the VRF Acme, and this is going to be associated with the VRF Beta. This way, it's going to essentially see them as two separate routing tables. So the routes that come from here have no idea on the existence of the routes that come from here. That's the idea. And internally, I'm going to use a protocol called MPBGP, which is essentially going to add route distinguishers and route targets in order to make my routes unique. So even though there are two prefixes which are essentially the same being announced on both of these routers, the routers themselves here in between, they will know what's the difference based on something called the route distinguisher and an extended IP address essentially. Now, I'm not going to go into much of the details of the networking here. This is just a very, very simple overview. Again, the idea is to go over the automation. So how do we begin to automate something like this, right? Well, the first idea is to begin looking at it step by step, right? I told you about a few components like OSPF and MPBGP, VRFs, and redistribution. Now, these can be used to make kind of a checklist on how to implement the service. I guess we can call it a network service. So here, this is what I have on the bottom here. Essentially, if I wanted to configure, let's say, an L3VPN for this site over here, for Acme Site 1, I would need to configure these things on this router and also on that router, because these are the two PE routers that connect to my sites for Acme, right? I would need to first create a VRF and associate my physical interface that connects to the client to that VRF. I would need to make an MPBGP neighborship between these two PE routers. I would need to configure the OSPF session neighborship between my PE router and my CE router. And I'll also need to redistribute. So I need to redistribute both ways, because as you saw in my example, I need to be able to input the routes that come from OSPF inside of BGP. And I also need to bring the routes that are coming from BGP and redistribute them back into OSPF. So I'll need to do this double redistribution on both ways. Now let's go to the code. But before we do that, here I have router 2 open. I have the terminal on this router over here. So this is a Cisco router. I'll show the running config real quickly. There isn't too much configured. I have a loopback interface, which is used for the internal OSPF. So here inside the MPLS core, I'm assuming all the routers are doing an OSPF in area 0. So everyone has IP connectivity to everyone else inside of the MPLS core. You also notice I have anyway some line configuration. What I wanted to show was the OSPF configuration, which uses this command MPLS LDP autoconfig. So this essentially enables MPLS on the interfaces that are linked to my OSPF process. Now this is routers 2 config. Nothing too complex yet. I do have BGP enabled on it, but notice that I don't have any neighbors, so I'm not sharing any route information just yet. Now, if we go over the code, let me begin by the main file, and we'll see how Nornir works. So this is where my execution begins, and usually I initialize Nornir with using a config file, right? Just so you know, this is what a config file for Nornir looks like. The idea for Nornir is that it's very pluggable, which means that you can replace components with ease. So here in this case, the component I'm using is the simple inventory, which is a YAML-based inventory. And here I'm providing some options to my plugin, such as the host file, group file, defaults, etc. These behave a lot like you would expect from Ansible. So host file is going to have host-specific variables. Group file is going to have variables specific to certain groups, and defaults is going to be defaults that apply to everyone, essentially, in case none of the above two apply. Additionally, you also have a runner configuration, and this is also plugin based, but you most likely will use the multi-threaded runner. Because again, this is one of the big advantages, I guess you would say, of using something like Nornir, is that you can do a lot of asynchronous tasks in parallel by using this multi-threading environment. So this way, a task that would take, I don't know, if you take like 30 seconds to access a router, execute some commands and go back, if you serialize all that, you're going to waste a lot of time. Whereas if you do it in parallel, you're going to essentially take 30 seconds all around because you do all of them at the same time. So this is the power of multi-threading. This is a very simple configuration file, but what's interesting is that once we initialize that, we have a NR object, which is a Python object that represents a few things. It represents our inventory. It also represents our current configuration. So if you open a Python terminal and try initializing a Nornir like this, you can usually see some very interesting data. So just to go into a very quick parenthesis, I'll just import init Nornir, and we'll initialize an NR object on this very same directory. So I'm going to be using the same configuration file and all, just to show you guys what it looks like. If I go into nr.inventory, you notice that I have a representation, of my current inventory, and this includes the hosts. So I have 5 hosts, a representation of the groups. I have 2 groups, the PE routers, the provider edge routers, and the P routers. Just let me show you the inventory real quickly. This is what a Nornir inventory looks like. So I'm representing it in YAML in this case. This is the information for router 1. So these variables are used for access. So for example, host name is the IP address that I'll use to access, or the FQDN. The username, password, port, platform, these are self-explanatory. In groups, I can specify a YAML list of groups. So if I wanted, I could keep adding like, I don't know, it's also a P router, for example. Connection options are going to be used by certain connection plugins. And in this case, I'm using netmiko. So here I'm specifying that whenever I netmiko connect to this device, I should be using the secret of Cisco. Because as you guys know, the Cisco router itself requires 2 passwords. So you need the user password, which you use to log in via SSH. And then when you type in enable, you also need to give in the enable password. So this is where I would provide the enable. And there's also some freeform data that I put in here under this data subtree. This is where we're going to keep custom variables. And this is very useful for modeling services and network-wide applications, I guess you could call it that. So this is an example. I'm specifying that my router 1 has router ID of this. It belongs to this BGP ASN, and it has this peer. So the peer 222 with customer Acme connected. This is going to be used by the templates, and the way I define my variables here is what I'll use later down the line in my templates. Now, going back from that little expedition, I guess we can go back to our main function now. And so here I have an object that represents my entire inventory. Here I'm just setting a variable to dry run. This is what I use in another function later down the line. But this essentially allows me to define whether or not I'll push configuration to the device, or whether or not I'll just push configuration to the device, or if I'll just simulate it and generate the templates. Now here, since I'm only doing my piece of automation on the PE routers, I don't really care about the P routers, in this case 3 and 4. I can just use this little method, which is called nr.filter, in order to filter for the groups containing P in their name. So in this case, I'm going to only get router 1, router 2, and router 5, which are the PE routers in this scenario. Once I have this, I now go into applying templates. So you notice that I'm doing this kind of in a template-based way. And by that, I mean that I'm essentially putting most of my logic inside of my templates, which are in the templates directory here. I have this little function, generate apply template. I pass it a Nornir type object. I pass it a template name. In this case, this is just a file name that maps to these file names over here. And the dry run variable, which says whether or not I want to simulate changes. If we look at this function definition, it receives a Nornir object and the template name, and it will attempt to generate templates based on what I provide on the file name. and then we'll try to apply those, so using another function. In Nornir, whenever you want to run tasks multi-threading, using the multi-threading framework, you're going to use this little construction called nr.run. So nr.run is going to receive a task. In this case, the task is called template file, and this is part of the Nornir Jinja 2 plugins. So this is essentially a task that's going to, for each host, open up a Jinja template and then render that template with the host variables available. So if we take a look at what happens here, I'll try to do my first execution. And you notice that I generated some templates. So what's going on here? Essentially, I ran my code up until here, entered this function here, and I try to apply the first template, iOS VRF add. If I take a look at this template, which is here, this is what it looks like. So for each one of my hosts, Nornir is opening a thread, and it's attempting to render this template. And in this case, it's looking for the variables under host.data.customers. And this is where my data model comes in. So if I go back to, just a second, if I go back to inventory hosts, you'll notice that for each router in the data section, I have a customers data structure here. This is a list of dictionaries. So again, since I have this dash symbol here, I have a list. I could continue my list by doing something like this, but inside each element of the list is going to be a dictionary, so key value, where key, for example, is name, etc. Looking inside this data structure, I see that for each customer in my customers structure, in my customers list, I'm going to render this block. So I'm rendering a block taking the customer name. Notice that Acme is coming up here. RD, which maps to this variable, is coming from this value. My route targets and route distinguishers come from here. And this template is essentially doing the first step in our L3VPN deployment. So it's creating a VRF. In this case, the name of the VRF is just the name of the customer, and is also associating that VRF to a physical interface. So in this case, my data model says that interface 00, fast Ethernet 00 on router 1, which is this interface here, is going to connect to my customer, which is called Acme. So on this port right here, and I'm going to give it this IP address. This is what's inputted directly on the CLI. So this is where all the values come from. I do the same thing for router 2. Since I only care about the Acme site right now, I'm only going to provide variables for Acme. So if I look at router 2, I only have the Acme customer under customers. And again, I'm also using fast Ethernet 00 on router 2. And I'm using the same route distinguisher and the same route target. In this case, I'm not taking beta into account, which is why I'm not configuring anything on router 5 right now. Notice that if I go down there to router 5, I have an empty data structure. So we'll add customer 2 later, but right now we'll just keep customer 1, so as to simplify this. Now, before I hit enter, I also want to show you guys what the rest of the function is going to do. So we came up until here. Essentially, Nornir generated the templates for each one of our hosts. In this case, we had 3 hosts because we filtered for router 2, router 1, and router 5. And then I printed the results. So this is what print results does. It creates this formatted output just like you would see in Ansible, for example. Now, since I'm not executing in dry run mode, I'm not going to enter here and leave. I'm instead going to enter this prompt, which is where I am right now. After that, if I press yes, I'm going to start applying configurations to my routers using this method here, apply template. Now, this is a custom task that I made myself. It's a very simple one. It's just going to take in, I can just go to definition. This is just going to take in a multi-result. That is an object with the results from the templating that I did on the previous task. I'm going to take the templated result, and then I'm going to transform that into a configuration that I can send via NetMiko. So here I'm just splitting the lines. I'm getting a NetMiko connection. In this case, this is how I'm initializing it. And once I have the connection set up, if the connection is down, I establish it again. So if the connection died for any reason. Once that is done, I enable and enter config mode. And then I begin sending a config set. After everything is done, I disconnect from the device. So essentially, this is going to take in all of these blocks of configuration and is going to apply them respectively to router 1 and also to router 2. So I'll hit yes, and we'll take a look at it happening. It's going to take in a few seconds. But once that is done, we should be able to see the configs being passed to the devices, and then another set of templates will be generated. Okay, so notice that we did create our configurations, and we can even confirm that by logging back to the router. So if I go enable again, show VRF, let's go for a show running config. You see that this VRF, which didn't exist before, now is part of my configuration. So the script itself just added that in this case on router 2. It also configured one of the physical interfaces. If we look at Fast Ethernet 00, I put the interface in VRF ACME and I associated an IP address. So the first step is done. Now the second step is to configure a BGP between our PE routers, which is what I can do on my second set of templates. So for a Cisco device, this is how I would configure BGP, MP BGP. So router BGP 65,000, excuse me. Here I'm configuring just a regular neighbor. I'm sending my loopback address just as a pseudo route to validate route transmission, and then I'm enabling VPN v4, which is what allows me to pass in route distinguishers, essentially to allow multiple copies, I guess you can say, of the same network to be transmitted, even though but coming from different sources. So I create this block on BGP for router 1 and the same block for router 2. Notice that router 2 points towards router 1 and router 1 points towards router 2, which is what we want to see. Just to show it off, again, the template looks exactly the same. So I'm just going to go over my peers in my data model, and I'll even show that because I didn't give too much context on the data model itself. So not only I have this customer's data structure, I also have these peers under BGP here. And this is where I define essentially the IP for my customer, the IP for my peer, excuse me, and any customers that may connect to it. So for example, in the case of R2, you notice that R2 is connected to two customers. It's connected to Beta and to Acme. So in order to allow these to coexist, I could have a structure like this. This is why the customer structure under here is a list. Now, I'm going to accept these changes once again. This is going to take yet another second. And once that is done, I should now see a BGP configuration block. So yeah, I have a new neighbor configured and address family VPN v4. I can even validate this by show IP BGP neighbors, for example. Notice that I have a neighborship configured with router 1. And if I go to router 1, I'm obviously going to see router 2 from there. Now this closes the second step. Now we're going to configure the OSPF between our customer router and our client router. I didn't go into much details on the client router. Sorry for the terminal. I don't think I can expand the font here. This is I think this is the GNS3 default terminal, but I'll do this very quickly. So I already configured the OSPF here on this router 6 in particular. So we're assuming that the client already done their configuration. Here, I configured my physical interfaces, put IP addresses, and I also configured the OSPF, as you can see here. Put a router ID, and I'm also sending some networks here. Additionally, I also have a loopback 200 interface here. In this case, I'm using this loopback interface, which is on OSPF, as a way to simulate a LAN. So just assume that whenever I receive this IP address on the other side, this means that I'm receiving the whole subnet, the /24 IP address, which is on this corporate LAN. Now, since we know that the customer edge routers are well configured, we'll just allow our script to generate the rest of the configuration. So here you notice that we applied the BGP, and now I'm looking into the OSPF configuration. So here I'm creating a process under VRF ACME with router ID, and I'm also associating one physical interface to that VRF and putting it inside of that OSPF area, that OSPF process. I'm doing this both on router 1 and on router 2. So let's allow that. And I should then see a log for OSPF adjacency coming up, because the moment I enable OSPF on this interface and on this interface, we're going to see some adjacencies. Now, the configuration was applied. Let me just check. So notice that I got a new OSPF neighborship through the interface fast Ethernet, which, as you remember, is the one that connects to our client network. Now that this is done, I can also validate the configuration once again. I should now see a second OSPF process on my show run, which is up here. Notice that the OSPF is under VRF ACME. But now that the third step is done, now we just need to do the last step, which is to do redistribution. Now, before we even try that, just let me show you the IP routes real quickly on my customer router on the ACME London site. Notice that the only routes that this router currently knows is the local LAN, so it can ping itself, for example, 1.1, but it cannot, as of right now, ping the 2.1 router, for example, which is in Rome. If I try doing something like this, you notice that I'm going to get a timeout. Now, here's how I'm going to fix that. And this is where BGP comes in, because right now what I'm doing is I'm receiving routes from OSPF via this OSPF from my ISP, but as of right now my ISP is not sending me any routes. So even though this router is sending routes to this one and this router is sending routes to this one, they are not redistributing the BGP routes back into OSPF. So this is what I'm going to fix with this last step. I'm going to make it so that the route for 192.168.2.0/24 coming from OSPF goes into BGP, and then once it reaches here, I'm going to put it back into OSPF. So this is why I do what I call the two ways redistribution. I do OSPF to BGP and BGP to OSPF. This is what I'm doing here in this template. So I'm generating a redistribution for process 100 from my BGP. And I'm also in my OSPF redistributing the subnets from BGP as well. Now, if I accept that, It's going to take a few seconds to apply, and later it will take a few seconds for the networks to converge. But what you'll notice is that I'll start receiving the prefixes from my remote site in my local one. Now, first, let's do a show running config and validate that those new blocks are there. Notice that under my VRF Acme address family, I now have a redistribute for OSPF, and my OSPF is also redistributing. My OSPF 100 is also redistributing the BGP subnets. So if I take a look at router 6 now, show IP route, you can see that I now magically began receiving routes towards the 192.168.2 network, which is this one over here. And again, because of this whole convoluted process, this is how we got this. So just as an example, 168.1.1, this is pinging locally. But if I do 2.1, then I'm pinging remotely. Notice that I now have IP connectivity between the LAN networks in my corporate sites. And again, this is all data model based. So if I want to edit this configuration, most of this is just going to be reapplied. So I can just change my data model and run the script again. And this is exactly what I do, because now that we did the Acme client, I also want to show you what it would be like to add a second client, so the beta client in this case. Let's go back to my demo. I'll go to inventory. I have a copy of this stage 2 configuration. This is what's going to contain essentially the same configuration, the same host configuration as before, except that now I added in the beta client. So in this case, I'm changing router 2 in order to add a second peer, because now router 2 needs to connect to router 5 as well. And I'm also adding a second client, because router 2 is also physically connected to a second client. This is on router 2, and I also added the configuration that was missing from router 5. So the peers, router 5 connects to 2, and the customers. So in this case, excuse me, let's just delete all of this and then read the host stage 2 file. So this should be the correct copy indeed. And I can just run the script again. Excuse me, python 3 main.py. Now you see that a few blocks of configuration changed. So router 1 is going to remain the same because we didn't change its data model at all. But what I did add was a second block of beta configuration. So I'm adding a second VRF to router 2, and I'm finally adding configuration to router 5. I'm going to accept this. And now that you guys at least have an idea of what this all is doing, I can go a little bit faster and just show you the results and then do some final considerations. Now this is applied. I'm going to do the same thing for the BGP, the MP BGP configuration. Notice I'm creating 2 neighborships from router 2. Configuring OSPF. And configuring the redistribution. Now, what we need to see is that router 6 is still going to keep working, so I'm still going to be able to ping the network on the Rome side for Acme, but I'm also now going to have routes being received at the beta site. So just let me check if it's already converged. Notice that we now have the 10 network here being received on my beta London site. Let's show up interface brief. The local IP address is 192.168.1.1. And here on the remote network, I actually have a .10 network. So 192.168.10.0/24 network. And this is being received through the exact same mechanism. So OSPF redistributing into MPBGP, and later redistributing once again into OSPF to reach our router. So now I have IP connectivity between both sides of my two clients in this case. And as you can see, this is relatively simple to scale. You would just need to manipulate data models and add new entries. Again, you'd probably need to work on it a little bit more in order to add the customization and other features. But once again, if you know my style of YouTubing, I essentially like to give you guys ideas and then let you guys play around with them. I also have a rollback script, just as a final example. And this is essentially going to undo all the changes. So it has the reversed kind of payloads or templates. In this guy, I'm going to consume the deletion templates, which I use to remove my clients in case I don't need any of this deployment anymore. So this is how I would remove a VRF, for example, in Jinja terminology. This is how I would remove my redistribution in particular. And if I go back to the rollback, you notice that I'm going to do the removals, I guess, in the opposite way, because first I was doing VRF, then BGP, then OSPF, then redistribution. Now I'm doing it on the other way around. So I'm doing redistribution first, removing, then removing OSPF, then removing BGP, and then removing the VRFs. And if I try to execute this rollback this time, are you sure you want to roll back? In this case, I'm going to say yes. And it's going to go through the same exact mechanism. So it's going to show me the templates, what it's going to do. I'm going to hit yes. So it's going to now try to remove the redistributions that it just configured. And the second I apply this and I wait for a little moment, you'll notice that I'll lose IP connectivity because I'll be undoing the redistributions, which are the mechanisms that allowed me to send routes from one side to another. Now that this is applied, if I try to redo my ping, notice that I lose IP connectivity. This is true for router 9, which is the beta London site. And this is also true for router 6, which is the Acme London router. Going to go through the rest of this, but you already got pretty much my idea. So here I'm just cleaning up configurations. Cleaning up the OSPF process and cleaning up the interface configurations. Removing the BGP. And removing the VRFs. I actually failed to remove the BGP, so what I'll do is I'll go into rollback mode again and just type Y here, just so that I don't skip that block. And if we take a look back at our routers, I'm going to access router 2 once again. If I look at its configuration, I clean most of it. So I remove the VRFs. Router 2 would need to have 2 VRFs. They were removed. I also removed any unnecessary interface configurations. Notice there's nothing under Fast Ethernet 0 and Fast Ethernet 1, which are the customer-facing interfaces. And notice that I do have BGP enabled, but I have removed all the neighbors. I'm not removing the whole BGP process because it could be that in some cases some other neighbors were configured. So just to remove exactly what is inputted from the service, I'm not removing the whole process itself. But yeah, with regards to Nornir, that's pretty much what I did. This was a cool little project. Got to learn a little bit about the tool. And if you guys are interested in this kind of content, again, please feel free to comment and like. and I'll make sure that I can keep bringing you guys some more network automation content like this. So thank you very much for watching, guys, and I'll see you next time. Bye bye.